Contents.
Yes.
So, like I said, we have the program and then the VM implementation. I'll start with a little bit of introduction about Canon, then the program, execution, some notes about running Canon, using it, some extras about a RISC-V version of this, and then we'll talk about integration and how we could use this and like combine it with the other projects. Next slide.
Oh, you're right. Yeah, I got you. Oh, wow.
Is it on? Oh, it's just off. Okay, so I want to start with this slide. There's always a applicable XKCD meme for any topic. There happens to be one about cannons, specifically building something like a fancy drill to make some holes in the wall. And then there's this other guy who basically says, we'll make 5 of them, we'll put them in a cannon, shoot them at the wall to drill the holes. And like we need to know how to use our tooling, we need to know what we are building. We don't want to be any one of these two people. Okay. So, actually, there we go. Okay. So, in our current rollup system, we have these different actors. They're all just like basically people, entities who run the layer 2 software, putting data from layer 1, watching layer 1. And so we have the sequencer taking information from layer 1. We have them produce layer 2 blocks. We have the batcher publish those blocks back to layer 1. The verifier putting layer 1 information down, now with batches to reconstruct the chain. We have the proposer claiming things about the layer 2 chain. And the proposer can be replaced by any user proposing something or claiming something about their withdrawals. And now we have this challenger, this new entity in the system that basically verifies what the proposer is doing. And to verify what we are doing here, and why we're calling it the challenger, is that it's interactive. We see what happens on layer 1, and then we compare it against our own local layer 2 state, and then we counter them. And until you hit some base case that Canon fulfills. So how does this look like? We have 2 functions. These were presented in the presentation by Ben. We have the simple step function that everybody knows. We take some state, create some post state. Now what we do with the dispute game is to just narrow this down to make this function as simple and as easy to represent on layer 1 as possible, down to just executing a single instruction. And then there's this pivot function. This is the interface to make claims about the layer 2 state. The dispute game doesn't know anything about layer 2. The pivot function exposes what is the state at any particular point in time in the trace based on the depth and based on an index. So this looks a little bit like this. The generalized index is a concept in the Ethereum specs and elsewhere where you can combine depth and index into just one integer with a leading bit. It looks like this. And for each one of these nodes in a tree, we can go 1 to the left and then right until you hit the bottom, where this is basically splitting the tree in half and determining the pivot point, determining the point that we use to bisect it to a smaller tree. And why like this? Why not commit to the full tree? We could do a commitment to like a full subtree, but this would mean that you have to know every single state, which is very inefficient. And if we're reconstructing VM states, we prefer to just produce a state at a certain instruction number, at a certain clock count essentially, rather than trying to commit to every single state that happens. The bisection game suffices with just a pivot point. So how does this look like with Canon? We have a pivot function which takes a depth, and like Ben described, up until a certain depth, say 20 for about 1 million block hashes, we return a block hash. Past that, we can return a VM state. So I'll talk a little bit about the Canon origin. So remember the bytecode checker, the past of Optimism, and then these projects from George to, I don't know, create a Binance bridge between a custom Ethereum fork, cheap ETH, Binance, or Optimism on cheap ETH, so layer 2 on a layer 1 fork, or even this RISC-V processor core that he programmed. Like these ideas combined into what later became Canon, along with these ideas about minimalism, about replacing L2GAF, about replacing the old Optimism with something that would express the layer 2 state transition in a clean and minimal way. So there's this, I think it's a discussion topic or something in this GitHub repository about the specs, where this idea is proposed and is kind of evolved from there. We later added the idea about splitting the consensus and execution to further isolate the changes from GAF, but this is really the start of it. So some of you might recognize the earlier pictures here. This is how Canon evolved. We had a simple Canon and then a more complex Canon, or more advanced Canon. Canon is trying to be simple. I think over time with the demos that were added, it got a little bit more complex than it needs to be. But it's all there. What we need to prove a transition of a Go program that happens to talk about Ethereum. And then what we're doing is we're making the next version of the Canon. The SolarPunk upgrade, or whatever we're going to call it, where Canon should be able to process the full layer 2 state transition in a production manner, which means that we'll have to work on the fault-proof program first, on the binary that we emulate, as well as productionize the virtual machine. This is the old version, the classic console with, I don't know, it's Nintendo 64, with this cartridge that you slot in, minigaf, the binary. There's this emulator thing on chain, mips.sol, and different ways to emulate it. It's really just interpreting the MIPS instructions. And then the challenger agent, where you could maybe plug in more challengers, but this is not just that scalable yet. But this is the general architecture, the idea of playing the game, literally the game, on-chain. So how do we do this? We have these modules, minigaf. This is the classic cartridge, the thing that defines the layer 1 EVM. Now, since then, we have had variants of this thing, not complete yet, not layer 2 compatible yet. We have MIPI-Go. MIPI-Go is the heart of taking any Go program and making it, slotting it into the MIPS machine. We have the MIPS EVM. This is the runtime, the thing that takes the Solidity contract, compiles it, and then emulates it. And there are two modes of this. I'll get into this later. And then there's the contracts directory with the smart contract that runs the instruction emulation. So this is what it looks like from the perspective of the demo, if you walk through the full repository. So from left to right, you have these ideas about creating a challenge and then with a fault or a simple correct one. And then there's this layer 2 on layer 2 variant, which is really just taking the layer 1 EVM and using layer 2 state instead. It's not yet the full derivation. But what it does, it's running these scripts that then run shell modules or other different things that do something with Canon. So first we deploy the contracts. We deploy whatever is necessary to run the game. Then we have some prefetching, getting the witness data to tell anything about the block that's being executed. So this is not just a single step. This is all the pre-image data you could possibly need. And then what it does, it calls into minigaf. Minigaf runs off-chain here first, collecting the witness data, collecting the snapshot and everything. The generation of the checkpoints done with MIPS EVM. So once we have prefetch data, we prepare the oracle, we have our binary that runs. We could create a snapshot of the pre-state, the thing that we we start from. And then we have a single on-chain step to apply on top to create a post state. And then, so with checkpoints, then challenge response, people fight over this, this step that's being executed. You assert that the step is correct at the very end. Now this demo, these scripts, it's kind of janky still, because we have many different target platforms, scripting languages, and things involved. When we productionize this, it should just be a single CLI library, like something that you just call on the command line. You say, I want the pre-state for step N, and I want the witness data for this thing to continue from there. But we can make that. And then I colored these specifically. The opgaf, opnode, main.go. These are the things we want to change in minigaf. Minigaf should be upgraded to support layer 2 by pulling in opgaf, the new gaf binary, the execution environment, and opnode, the consensus layer code that does the derivation, that takes layer 1 information and converts it into the attributes, the transaction list, going into the EVM. And main.go is like the thing that's gluing it together. So program prerequisites. We agree on the layer 1 chain. There's this starting point where the dispute basically anchors at the layer 1 history. So from there we can go traverse through all the pre-images to load necessary input data to produce layer 2 outcomes. Then for previously agreed layer 2 state, we need a pre-image oracle as well, not just layer 1, to fetch any layer 2 state. We're not reproducing all of the layer 2 chain in the MIPS EVM. We're just doing part of it. And then we have, well, the derivation, like the process that, that takes this data and produces the layer 2 outcomes, right? So this is what it looks like in a simplified manner. The layer 1 execution environment with our data. We have the layer 2 CL, this is the OP node, taking the layer 1 data, reading, extracting batches, and preparing inputs, preparing these attributes for the layer 2 execution environment. Then there's some state involved, and eventually it produces a useful output, something that we can extract and then post back to on layer 1. So this could look like a claim, or this is the thing you extract when you verify the claim. So agreed pre-state, this thing is like a given, but we do need to program to identify the agreed pre-state. The witness data should be on layer 1, so the program goes and asks the pre-image oracle for layer 1 data to convert into this. Other witness data is like previous layer 2 chain state. When we find the sync starting point, or when we work with layer 2 state, we need to load some previous layer 2 history. But then what we produce is like the disputed post state. This is the claim, or like the final outcome. So our program is like layer 1 chain, previous layer 2 chain, produce new layer 2 blocks, and then we extract outputs from the new layer 2 state. So we bootstrap, we find the starting point, which is the same starting point mechanism as we have for just when you boot up your OP node. It looks at your layer 2 chain, it looks at layer 1, it doesn't have a database, and figures out where it should start reading data from to derive the new missing data. And then we have the derivation pipeline. So this takes these layer 1 and layer 2 chains and produces the layer 2 blocks by first producing the attributes, and then converting the attributes using the execution engine into new layer 2 blocks. And by remembering the layer 2 state that we produce, we build this in-memory state database overlay over anything that we previously agreed on. And from this new layer 2 state data, we can extract the outputs. And the outputs, we extract them or we assert them. This is up for debate. There's no decision just yet. What we could do in Canon is to basically just halt or exit at a certain point, and then at a fixed position in the Canon state, we read the memory. We say, like, this is the final output. Or we could make the Canon state just do an assertion, where it's like a single bit of truth or like falsiness about the disputed root. The difference here is that whether or not we make the disputed data part of the inputs of this whole program. Because we could assert the thing outside of the default-proof program, but rather in the smart contracts themselves. I think it's more generic, more flexible to do it inside of the program. But because it's disputed data, you do need to confirm the root on layer 1 before you start generating the witness data. Okay, so this is what it looks like put together. I'm thinking we could start implementing this. I'll get into that. With the layer 1 start, this is like the yellow box. This is just a given where everything starts. Then we have the green stuff, which is like what we access through the preimage oracle. And then with blue, this means that there's some processing to do. So it's converting preimage data into useful arguments. And then when we have this derived data, when we know from the compute like what our dispute game is, like what the agreed layer 2 block is, what the disputed message is, this could all be part of the program. It doesn't have to happen on chain or on layer 1. We could take the data and we could compute it, we could process it by first finding the sync starting point, then deriving the new attributes, processing it in the layer 2 EVM, and then finally inspecting our new state, extracting the outputs. And this thing overall, this is just Go code. It's just putting together existing libraries, putting together the OP node, putting together OP-gaf, and expressing the synchronous state transition without the bells and whistles that the real node has. So there's no P2P networking, there's no API, there's no metrics endpoint, there's no nothing. It's just a synchronous processing function with pure inputs and this preimage oracle. And so let me talk about the building blocks. Like a lot of this is already there in the code base. We have the function to create the derivation pipeline. We have the function to find our sync starting point, given some abstract layer 1 chain and abstract layer 2 chain. These interfaces we can implement with like a lazy loading version of the layer 1 chain or the layer 2 chain, where if data is missing, we could like inquire the preimage oracle for the missing data. Then there's this step function. So once we have hooked up our inputs, it's just a matter of processing everything until it dries up, until there's no more new input. And then there's this engine, the thing that separates the derivation from the EVM. And I'll get to this. We can implement the EVM like this in memory pretty well. And then there is the final output route. Once we have produced the layer 2 state, we can grab the necessary data from the state and produce the output route as we know it in Bedrock. Or this could look in the future like extracting a withdrawal message or determining like the final output that is disputed. So to do one, mock the layer 1 chain. Mock it by hooking the preimage oracle to like our layer 1 interface. So we have this root of truth, the last layer 1 hash that we agree on. From there we could fetch all the history and we could expose the history with a simple interface. And this is the same interface that the OP node uses, but then attaches a layer 1 RPC client to. So this doesn't change anything about the consensus rules to implement. So we do the same for the layer 2 chain. The layer 2 chain is like the engine API and our trusty Ethereum block interface to fetch data by hash or by number or by label. When we say latest in the RPC, what we really mean is like latest agreed on layer 2 state. And it would start from like a point where the safe block matches the agreed layer 2 chain, and there's no unsafe data, it just matches the safe data, but we're producing the unsafe data and producing the new safe data by processing from layer 1. In action testing, we already have implemented a lot of this synchronous execution environment. So in action testing, this part of the end-to-end testing in Optimism, we have this ID of a layer 2 engine, and it really just wraps like the libraries from GAF, like the EVM instance, the chain instance, every source of data, and then extends it with this building interface to create new blocks. And then last but not least, so once we have our layer 2 state and we have these pretty interfaces to pull the state and the chain data from, we could extract the final output after completing the derivation, and we can compute the thing that has been disputed. Before we get in the preimage oracle, maybe I'll take a few questions. Then we have the preimage oracle, and then we can do a break, because then we finish the program state part, and then we can continue with the VM implementation. Kelvin.
I get the problem, right? So you need to put everything in the same process. Is that
Mm-hmm.
right?
You want to put everything in the same synchronous transition, because when we prove something, we don't want the environment with many external calls or data that's unavailable or concurrency. It needs to be simple to prove.
Okay, so you need miniget. Now,
yes.
Miniget is how simple can you make miniget? It's sort of, and don't answer this in terms of just use grunts, like a happy grunt is I can make it reasonably simple, and a sad grunt is really frustrating.
So minigaf right now, it's a copy of GAF where a lot of the GAF modules have been removed, which it adds simplicity, but it also adds a lot of maintenance cost. And so to really get it right, I think we should express the binary as a new Go module. And instead of stripping down the things that we don't need, we only import the things that we do need. And there's a nuance here, but it ends up with the same thing, that we have a binary of just the synchronous state transition that we care about, and not all of the other extras. So easy. It's relatively easy.
I guess not. Maybe it's a medium grunt then,
I mean, so the hard part will be this part. So this is not part of minigaf, and this is not part of the derivation pipeline. This is the part where we navigate to the dispute in the layer 1 data by introspecting the layer 1 state to determine what was agreed on. And that's a new interface. This is something that's not been implemented, and that requires a contract interface or something on layer 1 to expose what we start with. We could make a dummy version of this while it's not ready. It doesn't have to block the development of the other parts, but it's there. That's the harder part of the binary construction.
Okay. Yeah. I guess the core of my question was eventually, we want two things, right? We want this to be reasonably maintainable, and we also eventually want to build, an OP Aragon version of the same thing. And in grunts or whatever, how positive do you feel that those two things are achievable and not?
I think it's achievable, but we'll get into this. We can do the hackathon can cover this part.
Okay.
When we compile minigaf into MIPS, what impact does some of the Go runtime and other kind of nice things have on performance? For example, big int, right? That's going to cause...
There are certain things that affect performance, so it creates more instructions and there's more to prove. Now we are going to take a very generous approach in creating lots of capacity for the trace to run long. Mm-hmm. So even if we optimize minigaf, I don't think it biases very much, because I think with the worst case, we want to be very conservative and allow for many, many instructions to be proven.
I see.
But yeah, you could optimize the binary to create less instructions or less compute, and thus a smaller dispute game.
Got it. So the dispute game itself, the fact that we run it in so many rounds, obviates the need to optimize the instructions.
Right, and it's a logarithmic complexity, right? So having 2 times as many instructions just adds 1 step to the dispute game.
It's not that bad.
So we could maybe bias 1 step by optimizing it a lot, but we're not going to reduce it by 75% for another step.
Got it.
Is to figure out the way we access data from the VM. And how we do this is the preimage oracle. It allows us to load memory by authenticating it against the hash. And so in one atomic step, we can prove that certain data is there, is valid, is available, and can be looped into the project, into the program. So how does this look? This is an example of Canon. Canon has this beautiful thing with build tags, where if you compile minigaf for MIPS, it does the it does the on-chain thing. Where if you compile it with anything but MIPS, like x86 or another architecture, you end up basically running the program in prefetching mode, in like the mode that it loads the real data from an external endpoint. And so by prefetching, you can collect the pre-images. We'll get into that later. But by running in MIPS, you can just load the pre-images from this special memory mapped area. And what does this memory mapped area mean? This means that the virtual machine puts the prefetched data in the right position at the right time when the program requests the data. And it can request so by preparing a certain like hash or certain authentication data for the pre-image at the right location for the VM to detect what to insert. And so there's this function, like a helper function, that the minigaf state database calls into to load some state, requesting like some data by hash. And then in the non-MIPS version, we have the prefetching, preparing said data. So filling like the pre-images, this collection of data for the virtual machine to insert right when we need it to. Okay. So now if we put together the program and the pre-image oracle, we can familiarize ourselves with like the hardest parts of connecting this program to like a real environment. We can familiarize ourselves with Bedrock, with how that fits into Canon, making it Bedrock compatible. We could explore what this interface looks like that we talked about with the dispute game, like how we trigger the thing. And we don't yet have to know anything about the virtual machine environment just yet. Like we do need the interface, the pre-image oracle, the dispute game interface, the step function and the pivot function. We don't need the actual MIP stuff yet. So I suggest, like here, while we're here in Mexico, we could put this together and basically get a proof of concept running of this program that we're proving. Okay, now we get to the virtual machine part. Maybe I should stop for questions first about the program and the pre-image oracle. Quick questions? No questions? Okay.
Oh, sorry. So
There you go.
do we need the
Yeah,
microphone? Sounds good. So it's a small question, but like for this hackathon project specifically, what do you need in terms of the dispute game contract interfaces to basically be able to do the other steps?
Right, so let's go here. So this is the program that we talked about, and one of the questions already hit the part about what's the hardest part. Well, this is the hardest part, finding the dispute, interacting with the interface. And so when we instantiate, we start with a layer 1 block, which is after the dispute has been completed, or after the claim has been made of the pre-state. And then there's this question whether or not, or if we use the block hash bisection game to narrow down what we're trying to prove. If we do, then this means that we include the data that we have in the dispute game just before we hit the base case, so the previous steps where we dispute block hashes. And this means that you'd end up with a different instantiation of the virtual machine for every different base case that is played in the game, so that is more costly. We can maybe optimize it by only trying to do like a new VM per like upper like disputed block hash. We don't have to do that for the virtual machine dispute, of course. What I'm trying to say is that just introspecting layer 1 state, introspecting contract state to determine agreed upon pre-state, it's quite hard. It takes extra effort. And then only from there we can initialize the virtual machine.
Gotcha. That answers the question. Yep.
So just to say it again, like, am I right to say that you're saying that if we start at a agreed upon or assumed valid pre-state in L2, like a valid block hash in L2, if we assume that the pre-state is valid, then we can just execute pre-state to post-state, and that is pretty easy, including the pulling the inputs from L1, including the all the derivation required there. So the thing that we're like kind of abstracting away or like hiding under the in the closet is the complexity of finding the agreed upon layer 2 block hash.
Right.
So is that correct?
Kind of, yes. Where the most simple way would be not to introspect this too deep and to use a previously agreed upon layer 2 state, so like a previous output route. But say if we have many different withdrawal messages that each don't really commit to a block hash but to some withdrawal, then you really need the block hash information from the dispute game itself, which you only have just in time. Like it's some very recent data on layer 1 that has to be introspected into in the VM steps to dispute.
Yeah, but
so that's more challenging. But
yeah,
it could be done.
Got it. Okay, so like, for instance, one thing that we could do for like the simplified thing is assume we have a agreed upon L2 block hash, and then just as a POC calculate the next L2 block hash given the L1 chain. And we could probably do that for every L2 block hash independently.
So if we don't go into the withdrawal messages design just yet, and we stick with the output route design where there's only one output route every hour and it covers a whole lot of layer 2 blocks, then it's very easy to determine a pre-agreed on layer 2 state, and we can go and process from there.
Exactly. And then we can supply a withdrawal message, and then we make it a little different. Anyway, cool.
Anyway, but the beauty is that it can be part of the fault-proof program. So if we can express it cleanly in Go, then we don't have to put it all in a smart contract. Okay. Any other questions? I think this wraps up the program design. Now comes the fun part on how we get the program emulated. Like the program is basically just like generating the trace, and we have this pivot function in the dispute game design to pick any part of this trace. But then the last part is the step function, and the step function is emulating a single instruction to produce the next state. And like a single instruction as in single MIPS instruction, single RISC-V instruction, single WASM instruction, something that you could express as an execution trace. So I'll start talking more in a general way about how these VMs work, and then I'll get to like canon-specific things later. But to dumb it down, the simple execution environment really is just like no environment. There's no kernel, there's no hypervisor, there's no I/O, there's no parallelism, there's no privileged instructions, there are no complex instructions. We're talking about RISC instruction sets. We don't even use floating point numbers. We don't need a soft float library really if we only have integer operations like in Ethereum. So no environment is the way you could think about it. Note about floating point usage. Canon technically supports floating points, but it does so by just using the soft float compiler option. I am not aware of any actual floating point numbers in the miniGAF state transition. Maybe there's some metric in the Go runtime that could be a no-op, but in general, we could ignore. The Go compiler itself does not support this flag for other targets. So when we're talking about WASM or RISC-V, you cannot support it unless you plug it in yourself. Arbitrum, for example, they did the WASM thing, but then they have to go to additional like steps of like compiler steps to support these floating point numbers if they use them. But I would replace them with a no-op. Just keep them 0 or keep the current value. Don't try to interact with floats at all. Okay. So about instruction set architecture choices. So we have RISC-like instruction sets. George tried RISC-V first, but then shifted to MIPS. I'm sure there are various different reasons about tooling, testing, whatnot. George can probably explain it better than I can. But what the result was is a better choice with better support in the Go compiler at the time. RISC-V since then has improved. But like the Go compiler has supported MIPS for a very long time, whereas RISC-V support is relatively new. And then in MIPS, the beautiful thing, it's a RISC instruction architecture. So this means simple instructions that are very specific to a single purpose, that don't try to do a lot of things at once. So no multiplication and memory interactions in the same instruction. But this does mean that even though it's simple, we are still supporting general compute. We have to support 55 instructions and instructions, versions with immediates and without immediates. There's a lot to it. I'm not going to explain the MIPS spec in this presentation. I am going to explain canon. So if something is unclear about certain MIPS things, you can ask a question, but I'll try to stay away from the MIPS specific things and cover more about how we run through these instructions and the environmental stuff, the VM stuff. Okay. Any questions about architectures or instruction set targets? No questions? Okay. So this is the full list of instructions that's in canon. I had to reverse engineer this a little bit. So there is documentation for this, but then there are these pseudo instructions in all these architectures where the pseudo instructions really just interpreted as another instruction with a specific argument. And so when you implement this in Solidity or elsewhere, you only see the real instructions, not the pseudo instructions. So you have addition, your binary math, your unary bit operations, your jumps, shifting, pretty basic stuff. The most interesting one is probably the syscall. Syscalls are a special case where, like I said, there's no environment, there's no kernel, there's just nothing. And so the syscall operation, we hardwire to just support a few specific concepts that the Go runtime cannot run without. But past that, we don't really support syscalls. And then there are some atomic load and store instructions. There's no concurrency, so these things are pretty much just no-op except just doing the thing they describe. There's no atomicity, there's no fencing, there's no such thing as having to wait for instructions to complete. So these are pretty basic instructions. And then, like I said, sync does nothing. There's nothing to wait for. There's just a synchronous single thread. I looked into the Go compiler to really convince myself that canon covers everything that the Go compiler could output for the program, covers the instructions that we care about. I did the same for RISC-V. This is the Go compiler implements RISC-V and MIPS quite differently, to be honest. There are similarities, but the instruction sets, it's ghosting. Ghost printer. Let's go back. Actually, right. So, going to these instructions, you'll find the definitions of the registers and the instructions, but it is fully covered. And then what we know as a EOF library or loader, we have this binary that the Go compiler outputs, describing sections and segments. Sections are more conceptual. Segments are the literal things that contain the data. And these things we extract, we concatenate, and these are the pure MIPS instructions that the program needs to express what it's doing. The EOF output itself contains metadata and other things, for the environment to load, but we don't have an environment. So what do? Instead of implementing an EOF loader in our environment, we basically prepare the binary to be like executed from like a raw clean slate, rather than trying to support the EOF format in the EVM. And so how does this work? We first prepare the program data, we go and iterate the segments, we figure out how large the address space should be, and then we can allocate this program, like our concatenated segments, and this program we output as a binary file. Then later on, we could also iterate over the sections to get some debug data. This is optional. The segments is the only raw data that we have to support. Now, the EOF format does support like quirky things like filling a memory section or like a range of address space with more data than is actually defined in the EOF format. The Go runtime doesn't seem to do this, but we have to keep an eye on what kind of data we get in our EOF file, and if we can actually load it safely into this format that we need. So we might have to improve our EOF loading. Then this is the debug data I was talking about. So the EOF file contains sections. One of those things might be a symbol table with even more useful debug information. We can output this. It's not critical to the program binary, but it is useful information when you're trying to figure out where minigaf crashed or where the thing went wrong if we're making changes to the environment. About EOF, there's this abstraction leak from EOF definitions into the things you know as your arguments in your program, the argv, argc, and your auxiliary vectors. These auxiliary vectors, they're mostly optional. Now, Canon does explicitly define the page size as a hint to the Go runtime on how to work with memory. But what Canon does not do is defining the randomness. We could define this though, and what it gives us is that every time we run the binary, assuming there's no EOF loader who inserts its own randomness, you get the same result. And what happens now is that the Go runtime does get the same memory, and so it will derive the same randomness. But I think it's a cleaner thing to just explicitly define what our randomness vector is, so that we could replicate it outside of the special VM environment and in a regular Go environment outside of Canon.
Sorry, could you repeat, what is the randomness vector? What is it used for?
So, for example, there's this fast randomness function in the runtime of Go, and when you iterate maps, you get random iteration order over the map contents, because they don't want the map iteration order to be part of the public API. And so they use this fast randomness, and this is seeded optionally with this randomness vector. Okay. And so how do we go from like loaded segments to like full binary? We need this startup assembly prefix. What happens here is that we can replace the very start of the program so that we can start our program counter at 0, so that everything that the program starts at is 0. But then it will prepare our stack to contain these special arguments, these EOF auxiliary vectors, to have the correct stack pointer and to contain the initial data. A part of this is the enter point that's defined in the EOF. We have to jump from 0 or from wherever we start to the actual enter point in the program, so that the program counter is also correctly initialized. This is what the initial stack looks like in Canon. So once you start executing, you have these auxiliary vectors and basically just empty out the arrays that contain your program arguments. I think this could be a really neat opportunity to parameterize minigaf. Like if we want to insert data that the program starts with, we don't have to put it in a special memory range. We could just give it as a program argument if we put it in the right spot. Yeah. Okay, before I continue with more Go runtime things, Any questions about loading programs or EOF files or? No questions? Okay. Don't shy away from asking questions about like the more nitty-gritty things. So we have different Go compile targets, and I looked into TinyGo because supporting the Linux kernel at all is already too much in a way. We can support a subset of it. We don't really care about most syscalls. We only really care about a subset of the syscalls, which I'll get to. And so there are these different targets. The Go compiler supports the JavaScript WASM target. So this is what Arbitrum starts with in a way. But then like it comes with different complexity because it doesn't really support the full Go environment that you might expect. There's no Linux kernel, and there's no concurrency either in this target. It's kind of interesting, where it parks and then it unparks the thread to do certain Go things. We can work around that by only supporting a single thread and disabling other threads. But it's something to think about, where if we had a target that was synchronous and didn't have a kernel at all, it would be better. TinyGo provides this, but TinyGo is incomplete. It's a much younger project compared to Go itself.
I wasted a couple hours on TinyGo.
And George wasted a couple hours on TinyGo. It's an interesting thing, but it's not ready. So other alternatives, well, we have Canon supporting MIPS, and then I'm working on this project that does a lot of the things that Canon does, but then with a different instruction set. And I'll explain why after this presentation at the very end. But they can complement each other. And what I do is we catch the system calls that we care about, and we disable everything else.
Have that get compiled to its own like target.
So I don't want to use a tool chain that is deprecated or too esoteric. I much prefer the native Go toolchain rather than going through these old hoops that existed in Go to have an alternative compiler. I think the Go compiler it's right, and RISC-V support and MIP support is solid. So we can stick to a regular compiler without the extra toolchain thing. And with this extra toolchain, you'd still have the same target with Linux. Like you cannot work around that. And so I don't think it buys much in that regard.
Yeah, I agree. But just one point to those alternative chains, the particularly like the garbage collection aspect, the runtime, they're either non-existent or much minimized. So
the Go runtime, the Go code, defines garbage collection internally. It's not part of the compile toolchain. So we don't get rid of the thread that Go tries to start to run GC and all that. So using native toolchain or not, you end up with your common Linux target to have this type of garbage collection. Now there are certain parts of memory allocation that are like changed when you change the target. So like with JS WASM, you'll get some different properties there, but you'd still have the same problem. Okay, Sebastian.
So what's the estimated size of miniget after you do this transformation of the ELF?
So what's the estimated size of miniGAF? It's more or less the same size of the binary. So we do strip down it a little bit by not including like all debug information and all metadata, but the majority of the EOF file is just binary code. It's just data sections and code and everything that has to be there in the environment.
And in absolute terms?
In absolute terms, I'm not fully aware. It's probably like miniGAF. I'm not sure how stripped down it is, somewhere in the tens of kilobytes or more.
Okay,
But
tens of kilobytes.
like the runtime of Go is much larger than the program we're trying to execute. And a lot of the things we don't use, and maybe we can prune out, but I'm hesitant to try and optimize the thing. I'm not exactly sure what the current binary size is. Okay, enough about this target stuff. We have other things to cover. So from your computer science courses, you might remember this classic like diagram of your memory, where like the heap is allocated from the program break and then upwards, and the stack grows from the top. Canon works a lot like that, except the memory space is quite small, and a lot of the memory is used for special things. So the usable memory is very small. We have our program loaded at the very start. We have the program break, which moves up with the break syscall, so allocating some heap space. Then it can grow the heap with mmap syscalls. And then the stack starts somewhere and then grows down. The image here is not really reflecting the address space correctly, where this part of the memory is actually quite small. And this is because the MIPS instruction set and like the whole target doesn't really support like the full address space very flexibly. Like it has only like the signed UN32 or signed integer 32-bit numbers for the addresses. So you have to get 2 gigabytes of addressable space, part of which is dedicated to the preimage oracle, part of which is filled with our program, and then a small part of that is used by the Go runtime. And then the preimage oracle has to overlap with the Go runtime for the Go runtime to access the preimage oracle at all. So you don't really get to use much memory space. And then there's
If
one.
someone were to find an exploit, I think it was that.
Yeah, so George is commenting that.
Mess with the heap.
So George is commenting that we could pollute the heap with lots of data to have like a, like effectively like a buffer overflow, where you could escape the range of address space that's dedicated to Canon. For example, Canon has the special state that represents the register states, but it overlaps with the memory. So if you can grow your Go memory into this address space with registers, you could override registers and you could make arbitrary jumps using by escaping your application environment. This is really, really bad, and we want to have safety checks to make sure that Canon just aborts with error code if it ever grows memory out of this range. Would be a brilliant exploit though. And there's a special kernel page where the Linux kernel uses certain addresses to represent error codes and other things, and we as a program are not supposed to write to it. Okay, so I was hinting at these memory syscalls, break, which moves the program break. Canon just hardwires it to like only output one value, so you always get like a fixed amount of heap. But then mmap allows you to grow it further. Like say, okay, I want this much more memory. And the syscall, how it's used in Go, is you can state how much memory you need. And as an implementer of the syscall in Canon, we basically just give it the memory it asks without question. And so the memory allocation is questionable. We should put more safety checks in place. But it just means that we don't have to support the full Linux kernel, which is this whole other service we don't want. So all in all, I think it's a net win, but we do need to be careful about allocating memory. And so how this works is the syscall has certain arguments. These arguments, they're all placed in registers. Some of these registers we completely ignore. We know that we don't get any special values from the Go runtime. So like we're not going to do like memory sharing with other processes. We're not going to open files and do like memory mapped file reading. We don't need most of the functionality of the mmap syscall. We just need to allocate memory. Some other syscalls, we have 2 memory syscalls and 2 others. Exit group to exit the whole thing, to just mark the thing as done, and after that the state does not change anymore. And clone. Clone is a special case because we don't really support concurrency, but we do have to return the thread ID to pretend that there's this thread that matters. But it's effectively a no-op. And then Canon uses some other hacks with syscalls that are not implemented in the Solidity, but are implemented in the tooling to hint at certain actions. But I'll get to that in a later slide. So I'll tell a little bit more about hearts, parallelism, threads. So we have one CPU core, one hardware thread in RISC-V terms. Then logistically in Go, there's this model of processors, OS threads, and Go routines. And then Go routines, they're scheduled by the Go runtime to sit on certain threads. And then they can block or unlock. we need additional syscalls to be supported to really support this Go routine behavior fully. So we cannot afford an additional Go routine to be created. So we miss this functionality in Go. Part of this becomes like problematic because the Go runtime natively uses Go routines to do certain things, but we can disable those. So garbage collection, it's a separate Go routine started on a separate thread that we have to disable. And this means that the lifetime of the program has to be bounded, or otherwise it grows out of memory and you get certain problems. And so perhaps it's a wise decision to change canon from 32 bits to full 64 bit support, so that even though garbage collection is disabled, we have a lot more room to do larger computations that don't exit as early, and we can do more interesting things with that. Any questions about memory allocation? No questions? Okay. Okay, so step one to make it work is don't create a program that tries to use threads in any formal way. So don't try to read or write file handles, because these are blocking, and so they block the Go routine, and then the Go runtime will schedule something else, and then you get problems. So no locking. Locking is like a vtex syscall, and then you get a nightmare where the thread is parked until it's unlocked, and it's never going to be unlocked when there's no syscall to unlock it. And, well, pretty much don't do anything that requires a fork or like a clone. Then step two, remove the parts that are concurrent. There's this clever hack where when we prepare the EOF, when we say like Go binary output to canon binary input, we do this patch to disable garbage collection. So we look for the symbol that enables garbage collection, we find the function, and then we override the entry point of the function. So the garbage collection thing never runs. Amazing. It's the single binary lexicon. I think it's kind of impressive to support the Go runtime in synchronous way with just a single 8-byte patch. That exists. We could support garbage collection and concurrency, but making concurrency deterministic and supporting these additional syscalls. This is additional work and additional complexity, and perhaps not necessary if you have a large enough address space and everything is virtual anyway. But it could be interesting to support more advanced programs or to support programs that depend on this concurrent behavior. The state position of variance of concurrence, and you can play on the single synchronous thread. Okay, and I'll talk about previous oracle execution. So this is the other unsafe part of Go, where to interact with this previous oracle, we have to write and read memory. Writing memory is just a standard store version, like the different flavor snaps. Reading is the hard part. Reading means that we have to catch the address that's being read a certain range, and then we catch this, we can read the key from the special address, and then based on the key, we can copy our pre-image into the VM address that we want to use to expose the pre-image. So when we happen to read or load a few bytes from a special range, we have a certain range that we can read the length of the bytes from, and then the remainder, starting from that address, is used to read the pre-image. So this is a little bit of things I've gone to allocate the slice header at that specific range of memory. Carl.
I just want to chill this previous thing. I know we talked about the pre-image oracle before, but I just want to mention just how insanely magical it is to have the ability to write a 32-byte value and then retrieve literally any known pre-image to like mankind. And this actually gets at a very fundamental property that the Ethereum that blockchains provide us. And I would basically say that the fundamental thing that is most important that a blockchain provides us is it provides us a single hash which is the latest block hash, and then a structure of how that block hash relates to various pre-images that you can then use the pre-image oracle to generate. Like this unlocks, if you start with the latest block hash, you can pull in any block hash in the history, any state at any block hash in the history, any hash in the state that is committed to, that is made available in some out-of-band context. This is the property. This is like what is really meant when we say data availability. That is what it is.
Right. And so this covers the parts of the Go code that interacts with Oracle. The VM itself, I'll get to that, exposes the pre-image, it serves it, and there's more to do like prefetching and all that. Okay. So how do we pitch that there's something interesting at our memory maps that are in the address space? Well, we run a system call in Go. The system call is a null. It's like we get the process ID, but we don't do anything with the process ID. What the tooling around can pick up on is that the previous oracle is dirty. There's some key, and that there's now a range of values that has to be represented with the new pre-image. So this is the simple hack to make the environment aware of the need for a pre-image change.
Yes, from Calvin.
Okay, so you use the get PID syscall as just a flag for the environment. It says, hey, you need to update this.
Right.
And then what?
And then the environment
literally modifies the state of the VM to include the data in the.
more or less, yes. That's kind of what happens.
Okay, so it just writes it into the memory, and then the way you emulate this on chain
Is by catching the load instructions onto this memory, and then mocking the result of that load.
Right.
And the effect is that in the tooling you don't have to watch every single instruction to insert a pre-image. You get to do something more efficient by doing this system call thing, and it doesn't add much overhead because it's a single instruction that we are adding to signal the thing. But then on-chain we'd rather not have to like interact between loads and syscalls to make this work. We just want to load the right data right away. And so when you load the pre-image, you don't actually load the full thing at a time. What you happen to do is you identify the pre-image by loading from that range and reading the memory mapped key, but then only part of the value is loaded. And all of the other part, the rest of the value is just dropped again. Like it exists in the contract, but it's not moved into the VM. Just like a load instruction only loads a few bytes at a time. Okay. So this is the in the tooling how we do the process ID hack. We detect our syscall, then we check the oracle hash or the pre-image hash, and then we read a file from the file system with our pre-image, and then we prepare the result, or like the memory to load it from. So this way we can reproduce the same pre-image behavior in a VM like Unicorn, like some instrumented MIPS emulator to do the same thing. Okay, almost there. So this previous section was more about like how does this work in general. This section is more like how does it work in Canon specifically, what are like the blockchain tweaks, because like the previous section could have been any emulation environment. Now we're getting to more of the on-chain stuff. So memory in Canon currently, and I'm not sure if it will be in the future, is represented with a Merkle-Petitjean trie, just like the Ethereum state. In a way, this makes sense because memory, although it's a contiguous range, it is all kind of sparse. We don't need all the memory at the same time. But the Merkle-Petitjean trie is also very bug-prone, and using this as our representation to commit to memory on-chain is not that fun. It's bug-prone. It's one more library to audit. And so I think we should replace it with a more simple tree, perhaps a binary tree where there's no difference between a zeroed leaf value and a non-existent leaf value, to really have clean zeroed memory from the start. But that captures the idea where the Merkle-Patricia trie, it's a solution, it commits to our memory, we can verify one piece of memory at a time with that proof, but we probably don't want to depend on this long term. And so, having memory in place, we have this hack where we don't have to do the same thing for registers separately. Instead, we could just represent the registers in memory. Like we could copy the register state into memory every instruction, and that way the register state is always committed to and can be safely accessed from within Solidity by just reading these special addresses. And so we read all our MIPS standard registers, and on top of those, we have a few special MIPS registers for the result of like a multiplication upper hand output, like overflows and things like that. But more importantly, also the heap value. The heap value is the current state of the mmap, the current state on like how much memory have we allocated already, and then from there more memory is allocated on subsequent system calls. So that's where registers go in Canon. And we can change that as well, where we don't have to stick to these special addresses to represent our registers. We could separate it more cleanly to not have this danger of overlapping memory usage and register usage. But yeah, this is the current state of Canon. Okay, so having this Merkle-Patricia trie off-chain also means that we have to do these proofs on-chain to access our data. Now, this is the interface that mipsmemory.sol exposes. So we have generic functions for writing and reading memory. And when you're writing memory, essentially what you're doing is you're taking the previous state hash, your mutation, and you output a new state hash. And so this is the state after you apply the changes to it. And so you only need a proof for the branch that you're mutating. You don't need to represent or load any of the other memory. Read memory is just a subset of that. You prove that the thing you're reading. And then the preimage oracle stuff is the harder part, where we're not interacting with the Merkle-Patricia trie directly, but instead we're like a shim. We're like catching the read in the load instruction, and then instead of calling the read memory function, we call the get preimage oracle function to get like 4 bytes of preimage data from memory, or from from our preimage memory. So there's a function to load preimages into the system before you run the thing, and then there are the functions that the mips.sol thing uses to access the preimage data. And then there's a special thing for large preimages, which I'll describe later. But first we cover the mips.sol. So the on-chain MIPS implementation is actually so simple that it fits in this one slide. This is all that there's to it. The ugly part is that the ALU is actually more complicated. It's a pure function, but it does take like an instruction, registers, memory, and output and result. And this thing is like a big switch statement to do the MIPS transition for the most part. The other parts are just like preparation, like reading the instruction, reading memory inputs, and like post-processing to write our results back to memory. And a special thing to catch the system calls. Any questions about mips.sol? Maybe during the hackathon we have some time to look at this part of as well. We could extend testing, or we could try and support like additional instructions for 64-bit support. But I think we first focus on the fault-proof program itself that we run in this virtual machine before we improve the virtual machine. No questions? Okay. So this is how syscalls work on-chain. It's another switch statement where we detect the type of the system call. So we have mmap, we have breaks, we have clones, and we have exits. mmap is the bulk of the complexity, where with mmap we want to figure out if we have a hint or like where the memory should go, or if we have like no hint and we just say allocate it on top of the heap. Break is just setting the program break, that's hardwired. Clone is just returning the thread ID, that's also just a constant. And exit stops the whole thing and just marks the things as done. So complexity is quite limited. We don't have to support the full Linux kernel like certain other optimistic rollup-like projects do. Which is interesting to support a whole lot more programs, but it's a lot more things to do and support on-chain. Okay, and so the preimage oracle, it's like the key is written to memory, but the preimage, when it be loaded from memory, it's not actually the memory. It's like this shim on top to get the preimage data. I kind of already went through this. But that's how it works in the smart contract to avoid interacting with the memory at all. Like we don't need to interact with the Merkle-Petitjean trie. Okay, last but not least, the large preimage oracle problem. So there's this condition where if you have this preimage oracle, you need to load things into the oracle. Loading things into the oracle can be quite complicated when the thing that you're trying to load is larger than the capacity of the environment you're trying to load it into. And so layer 1 can have like huge receipts, can have huge transactions, and these can be larger than layer 1 itself can ingest. Like by definition, the layer 1 transaction will always be larger than the maximum call data that can be supported in a single transaction, just because the transaction adds a signature and other things. And so we have this limitation where we cannot trust the layer 1 environment with our preimage oracle, and we just need to work around this oracle problem where we need to load part of the transaction instead of the whole thing at once. And we can do so if we had like a chunk by chunk processing thing. This is implemented in Canon and works. It's not pretty because it does have to process the full hash digest one chunk at a time before it becomes usable in the VM. But it's a start. Then an alternative could be a ZK proof, where you prove equivalence between a regular hash and a Merkleized hash. And then the Merkle root can basically help you access data of the preimage at smaller bits at a time by just providing a Merkle proof. And then last but not least, these Merkle proofs could be native to layer 1. There's this initiative to improve the transaction typing to go from RLP to SSE, which solves the preimage oracle problem and many layer 2 problems in general, where layer 2s have much less trouble proving layer 1 data. They're just making the layer 1 data more amenable to proving. I want to highlight some Canon implementation risks. So this is a research project as of now. We're productionizing it. But to productionize it, we need to understand risks. One of these risks is that Canon has two completely different environments to run in. And so any difference here might become like a divergence thing where somebody might think they have a valid answer, but they don't actually have a valid answer to the layer 1 result or to the layer 1 expectation of the MIPS instruction. And so we need to closely analyze the differences there. And then we talked about the memory and registers overlap, where together with limited memory space, we really do need some safeguards in place for application data to not escape the Canon virtual machine. And then we need more testing. So Canon does pass some standard MIPS instruction tests from Berkeley, but there could be more testing. We could utilize fuzzing to compare different MIPS emulators to really be sure that ours matches the standard. And then the Go runtime can behave in unexpected ways when we don't really support all Go runtime functionality. So looking closely at the compiler and understanding which MIPS features are being used by Go helps us cover all of those. And then the Merkle-Petitjean trie, I think we should swap it out. It's not the highest priority thing to swap out, as in it works, but for production, it's not the best thing to have. Okay, we're getting close to the end. I want to leave you with some canon notes on like how to run this thing or how to understand this thing, because so far we've only been abstractly talking about what it is and how it works. So there's this demo thing in Canon. I touched on this in the diagram at the start. We have all these different modules, but it boils down to a layer 1 EVM proof. There does exist this layer 2 and layer 2 demo, but what it really does is just EVM transition. So it proves that it's viable for Ethereum, but what it doesn't do is access the layer 1 data and run derivation. So we have to fix the program that we're fault-proofing before we can really run a sensible demo. And then there are different run types in Canon. So we have the Unicorn, EVM, and chain types. Unicorn is an existing emulator that runs in Go and also in other languages, but it essentially allows you to hook into it and substitute or extend different functionality. The most important here is the system call overrides, where if there's a system call, we make some changes to the virtual machine to emulate what the Linux kernel would have done. Then the EVM uses the compiled smart contract, but then it stubs out the actual access to the on-chain storage. And so it runs much faster than a real chain environment, which is the last option. EVM, I think it's not the right balance between these two solutions. I still like to stub more of the memory, more of the things to make it even faster. But it comes with trade-offs because we do want this thing to be as much as the chain as possible to get more testing in with a real environment. Because this is the thing that runs in production. This is the thing that we have to trust to produce correct results. And that's the thing that interacts only with compiled contracts from source code. And like no special hooks or no callbacks, no nothing. Questions about the different run types? No? So I described these modules in Canon earlier. So I have to go back a whole lot of slides. But essentially MIPI-Go is like the Go tooling to go from binary of miniGAF to a thing that's executable. MIPS EVM is the thing that allows you to run these different types of tests and make your own custom demo, essentially, by running the virtual machine. Okay, so this is a short extension to the presentation. Like we have 70-something slides. There's only a few about asterisks. Asterisk is a RISC-V version of Canon. So it's not a replacement to the fault-proof program. Program is the same, except that you compile the program towards a RISC-V target instead of a MIPS target. And why RISC-V? If you remember from the start of the presentation, there was this Nintendo 64 thing with the cartridge in it and the controller for the Challenger. Now, we want to upgrade Canon to be a newer console, like have a new interface for the Challenger. But you could have a second one and a third one and so on. And we could have more than just one fault-proof program to run, right? So minigaf.bin was the original. We can have mainnet.bin or something for Optimism mainnet to prove. But we could have an alternative chain that we do fault-proofs for as well. We could extend the stack and provide fault-proof services to more than just Optimism mainnet. And then by doing so, we have like this store of games we could load into our environments. And we could have different interactive environments. We could have less interactive environments that are more expensive to run, but maybe are more useful in other ways, like a ZK proofer. So no controller, no games, but fulfilling the task of verifying a game. And then, last but not least, the most popular games are cross-platform. So if you go back to the previous slide, all these things you can play on multiple consoles. They're not limited to just one fault-proof environment. If you can play them on multiple places, you can challenge them on multiple places. You can have a quorum, you can have like a multisig-like behavior between different computers. So we can remove systems, remove humans from the system, and just have agreement between different fault proofs to hedge against bugs in any one of these platforms, but to have a collective that can prove any type of state transition. And so the differences are, I went straight to 64-bit support with asterisk. Asterisk mirrors the Go and Solidity syntactically. It's like trying to make the implementations look so similar that it's very easy to audit one and then cross-verify the other one. Then I don't use a Merkle-Petitjean trie for asterisk, just use a binary tree. And then instead of trying to prove a whole lot about memory in the same step, I only do little bits at a time to try and simplify the process. Asterisk has no floating point support at all. Like there's no soft float, it's just a no-op. And asterisk, compared to Canon, it's much more experimental still, where the on-chain version is not complete. Just a week ago, I got standard RISC-V tests passing, but we're not there yet. We have lots more testing to do. This is the architecture of asterisk. So we have a Go version of the system and a Solidity version of the system. The Go version has two different variants, the fast one and the slow one. They all have an ALU, like a expression of the instruction set, of the computations, that are really, really similar. It's like minor differences between Solidity and Go to get the syntax right, but the if statements and everything is the same. And so that's easy to cross-verify, but you get to use different backends. You get to use like UN64 natively, or you use a Go like 32-byte integer to represent the UN64, but to prepare the pre-images for the on-chain environment. And then the Solidity version has UN256 as well. And there's this fun thing where Solidity over time changed, became more safe, but harder to use for low-level things. Like overflows, they're a feature, not a bug. Like overflows are native behavior, part of MIPS. Like integers work the same. Overflows are part of the behavior spec. So we can use U to express like the pure computational parts cleanly in function calls to functions that match the Go implementations. So when you read the implementation of the ALU, you don't actually see like operators like plus signs and minus signs, but you just see function calls. And these function calls are backed by these different variants. And then last but not least, we have the raw state. So this is not Merkleized at all. This is pure memory, super fast. Then we have an Oracle version of that. So this is Merkleized and much slower. And then we have the on-chain state, which uses this, but only by first preparing the pre-image state and then fetching it. So this is what the fast mode looks like. It's really simple. You load your EOF. EOF loading is integrated, so it's no separate tooling, no mess with Python. You can just write a test case where you load the EOF and you run your step function through a whole lot of steps, and then you stop when the VM exits or when you hit some sanity count if you never hit the exit condition. And then the slower version, or like the full demo, there's more code. But in summary, we do the same thing as we just did with the fast version. We load EOF, we run fast till step n. This would look the same in Canon, where up until instruction n, you just run through the VM as fast as possible. Then you stop, and then you start preparing your virtual machine to capture the witness data that you need. You just do one instruction, and every witness that you collect, you memorize to use it again when you run the on-chain version. So this is your data that you have to supply, like an access list, to the on-chain execution. So this is what the full thing would look like. To load EOF, run fast, run slow, create access lists, and then run the on-chain thing. But it's still readable. It's like a single file to run it end to end. So there are some to-dos. I need to implement the pre-image oracle. I'm not shimming the reads just yet. So when there's a load to a certain address, I'm not trying to hook to a pre-image just yet. I want to utilize my testing for all modes, also the on-chain version of Asterisk. There are some EOF loading improvements to do. So right now we have this thing in Canon that's like a standalone, it prepares a binary. We have this thing in Asterisk which does ELF loading, but does not do the startup.s file, like the assembly. That's skipped. It just takes the entry point, loads it into the VM. There's this in-between version where we can cleanly initialize the binary that we execute. Then finish the on-chain version. And then maybe, but this is like a stretch goal, we could support more system calls to do like locking and concurrency and other things, which could widen like the use case for Asterisk a lot more to new like platforms. So it's not just Ethereum, but like other concurrent environments. Okay, last slide basically. I know we're all tired. The dispute game and the fault-proof program CLI. Ben described this like this interface with like a pivot and a step function. The pivot function just needs you to identify a claim for any point in time. So here we would just run Canon or Asterisk in fast mode straight to that instruction. Maybe we can do some checkpointing to reuse work. But essentially, you just want to get to that point in time that we want to claim ASAP. And then once we reach that point, once we have identified our final pivot, then we can do a single step the slow way and produce the witness data to reproduce it then on-chain. So our interface for the CLI could really just be 2 commands. And then improve Canon data. So Canon, there's some improvements we could do. I want to focus more on like tooling, enabling things to be more debuggable, easier to analyze, so future changes are easier. So this could mean like ELF sections and symbols table, or visualizations, or dumping the VM state in a more readable format. All these things are very useful to use Canon. And then the very last slide, testing. Differential fuzzing must be like it's a must. So between Canon, Asterisk, any fault-proof target, we should have a more like general fuzzing test setup so that we can compare all these different variants of the virtual machine and see if they all make sense. If they agree, then the chances of a bug in one of them is very, very small. Okay, and then, yeah, I want to automate Canon. I don't think we'll deploy it on-chain just yet, but just reproducing the default proofs off-chain based on real events that happen on-chain could showcase the readiness of Canon. And then we can debug, see how it works, and at some point we can be confident in pushing this to mainnet without surprises. Okay, we're there. This is the exit. Exit call. VM closes. We're done.
Yes.